it live. This recording is for the other classes who are going to miss tomorrow. Yes. Everybody gets really quiet. All right. All right, so we're going to take a look, just kind of going back and recapping a little bit of what we talked about before, just so I have a complete set of notes depending on where I stopped in my other classes. We started talking about the idea of extrema. Extrema, we're looking for the highest y value on the graph or the lowest y value on the graph. There are two things that we're interested in, the actual max value and then the location of the max value. What is the actual max value? The y value. The location is the x value. Okay, so we want to make sure we pay attention to that kind of distinction. We have our absolute and global maxes and mins. The y value for which there are none higher, the y value for which there are none lower. Which means there can be more than one location at which you have the max, but you can only have one actual max value that you're going to be looking at. And so we kind of went through the notes and we talked about that in our first example. Given all the green dots, you have a selection of points that may or may not be your absolute max. And then again, kind of to stress to you and everyone else, the global max is actually, why is it G of D? Because it's the y value at x equal to d. That's our notation for the y value. The max value is the y value, and then where it happens to be at the x value of x equal to d. Okay? And then the global min, same reasoning. The global min is the y value at a over here. So that's the lowest on this function, and then the highest on this function. Yes? Well, you would just, that's why you can say G of x for x element of, and then put the interval for which it's there. Because every point, because remember it says there's none higher. So you can be a point on that line, and all the ones adjacent to it, there's none higher, so it's still considered a max on that line. Okay? All right, so everybody good with the whole global and AKA absolute maxes and mins? All right, and then so we went through several examples down here at the bottom where we were identifying maxes and mins. Sometimes we have both, sometimes we have none, sometimes we have one or the other. A couple of comments about this. When there is a hole at a location where you would like to say there is a max value, why is there no global max? Well, there's always, you pick a y value that is actually a y value on a point on the graph. And maybe you pick the one right here. Can somebody pick one higher? If I get a little closer, can you pick one higher? Yeah. It doesn't matter how close I get to that non-existent point, because how many points are there on a little curve or any type of a line? Infinite, there's always one a little higher. So you can't actually physically pick a y value for which there are none higher, so we say there is no global max. Another way to think about it is that the highest point as a whole is not really a point on the graph, so therefore can't be a candidate for an absolute. Patrick, put that up. Whatever it is you're doing, pay attention. All right. Over here on this side, we had no global max here, but for a different reason. Why did this scenario have no global max? It goes to infinity, and remember, I'm looking for a y value for which there are none higher. Can you name a y value? No, infinity is not a y value. Infinity is a destination, not a y value. There is no y value that I can name for which there are none higher, because if you name a y value, I can name one higher, because it continues its ongoing travel to infinity, so I could pick another one. So we never have a global max. And again, why does this not have a global min? You have the hole at the bottom, non-existent, so therefore we have no global min on that one as well. Over here on this one, we had both a global max and a global min, and again, I don't know, there's no values over here for the y, so I don't know what the y value actually is, but the max is the y value, and so we use our function notation to name the y value. The global max is, all right, don't start doing that stuff. The global max is the y value at x equal to 2. All right, and in the last example that we were taking a look at over here, we had both a max and a min, and it was nice and easy because it happened at one of these little vertex points here and here. All right, any questions on absolute maxes and mins? And also, why did the range look like this for this graph down here at the bottom? Because why am I using f of 0? Because I don't know the y value. I have to say, well, I need the y value at 0 because 0 is the location of the lowest point that's there. So I got to put in the y value. I don't know what it is, so I'll just name it f of 0. I had to make up something for k. I had to make this up as k. Why did I have to make that one up in this problem? Yeah, we don't have a notation for a hole. F of 1 is this point right here, not that point. So you're like, well, how do I name that one? Well, I don't really have a notation for it, so I have to say, okay, the location of this hole has the coordinate 1k, so that I could then use that to kind of talk about what the range is. I don't know what number that was. Hopefully, if we were actually doing range, you would know specific numbers on this. All right, and then see, what else have we done last time? Oh, and then we had this whole constant function, the special case of when we were looking at extrema. And again, the idea is that we're not saying there is a single highest point. We're saying there is a y value for which there are none higher. So every single point on this line, or this segment, has a y value of 5. Are there any y values higher than 5? No. So 5 is a y value for which there are none higher. Therefore, it is a global max. However, it occurs at infinitely many x values, and so we change this over and we start going at, instead of x equals, I make it x and element of, and kind of go all the way across. And then we have our, it's also, 5 is the only y value, so not only are there none higher, there are none lower, so it also counts as a global min. And so that's weird, so weird, but that's how it works by our definition. Then we switch gears a little bit and we come down here to relative extrema, which means that we're not looking at the entire graph, whole picture from beginning to end. We're only looking at a kind of a snapshot picture of a little region, a local area. We're zooming into the city level, okay? Instead of looking at the whole United States, I'm going to come in, zoom in, look at a city, and then look at what's going on for that region down here. It's called relative or local extrema. So the first thing is notice that we have to have an open interval that contains the point of interest, the location that I am looking at, and that you have to make sure that you have a left, there has to be graph to the left of that location, and there has to be graph on the right of that location, because you can only be a relative max or min in comparison to what came before and what came after that location. So you're doing a comparison to the left and to the right. And so, and if you look to the left and everything on the left is lower and everything on the right is lower as well, then we know that we have a relative max. Okay? On the interval, if I kind of, it's almost very similar to global. It's just saying, well, if I ignore the rest of the graph, would that be a high point on the graph, a global max? If that answer is yes, then it's a relative. Okay? And so we have that going on. If you are in relative max, you may not be the absolute max on the graph, because there may be other locations, and sometimes here you want to show absolute relative that is the highest point over there. Okay? So, yes.
How do you impact the circle?
It's actually a great area. You just have to have a little bit of a loss
a little bit, because like I put this example up here, and you might want to say that there's no left side to this, because you guys see, hey, the piece comes in, and then I'm right here, and then there's nothing on the right side. I'm like, oh yes, there is something on the right side. It just doesn't happen to be connected. What word do we use for that? It's not continuous. I'm not saying it has to be continuous, something on the left, something on the right. I'm saying that there have to be y values for the x's to the left and y values for the x's to the right, so I can do a comparison. This y value at that x value, we'll call it c for the moment, at x equal to c, this y value is here. Look at the y values of all the points on the right side. Are they higher or lower? They are lower. It has all these little y values going down. If I look at all the y values for the points for the x's to the left of it, those values are down here. But those values are lower. And that's what you're looking for. At x equal to c, that y value is higher than the y values of all the points to the left and the right of it. Yes? Or like we had a piecewise function, came in maybe here, and then has a regional discontinuity, and then starts again here and then goes down, then you have a problem. That cannot be a relative extrema, because I have nothing to the left of it to compare to. Okay? It's kind of a weird special case. And that has to do with our comment that relative extrema cannot be endpoints. And what I mean by endpoints, it means if there's nothing on the left. It's kind of, I probably shouldn't say endpoints. It's can't be next to a regional discontinuity. Maybe that's what I want to say. Because if you have other stuff missing and nothing missing on the other side, it can't be a relative extrema. And that's a very formal calculus definition too. Because there probably are some pre-calc books that will let you call that a relative extrema, but in calculus it's not. So we'll go with that. If the line went up, kind of had a constant section, like that, yes. You would have the same kind of idea where I'd say, well, suppose this was 5. And this value was 1, and this one is 4. Okay? If I was looking at this, I'd say, is there relative maxes on this graph? The answer is, yeah, the relative max is 5, and it happens for x is an element of 1 to 4, inclusive. Okay? Now, it does get a little kind of weird when we start a little bit more technical. What if that piece right there went up? Are there relative maxes? Yes. On this section of the graph, okay, there is a relative max. Okay? Now, what's going to make it weird is, let's see what the difference is between the other one. On the other one, I said y equal to 5 is a relative max, and when it went down, it was 4x, an element of 1 to 4 with brackets. That's what it was. Well, now I start going, okay, relative maxes. Would this point still be a relative max at 1? Yeah, because if I look to the left and the right, to the left they go down, they're below, and on the right they're the same. So it's still a relative max. Every point in here is still a relative max, because if I can look, it doesn't matter how close I get to this point here, because that point is still a little bit to the right. That counts as I have graph to the right to compare it to. What happens when I get to that point, though? Is that a relative max anymore? No, because if I look directly to the right of that value, there are points that go above as opposed to going below. So we would change it, and if I was doing this graph, I'd have to make this a parenthesis, because there's not going to be a relative max there. Yes? Okay. You just have one y value that's a max that happens at 2 locations. Okay? And that's okay, because we're just looking for the y value for which there are none higher. But it could happen in more than one place. Now, usually you just say, if it's only like a list of a couple of places, usually just go 5 is the relative max at x equal to 2 and 3. And just walk away from it from that. Yeah.
So right here, like, is feet, and at the top of the book, or front, and then I think that is part of the open center. So that's more fun.
Well, you would have a relative max here, a relative min here. I would have no global max because the candidate that would be the choice for the global max up here is not a point. Okay. Is there global min on this one? No. Okay. All right. Is that helping kind of clarify all the max min stuff? All right. So we did that. So we talked about that. Again, this is super important. Relative extrema must have function values, points, y values, left and right of x. And that's really just for the comparison. Because you can't be a relative max unless you know that the stuff that came before the stuff that came after. And it doesn't have to be a big section of the graph. Just have a little bit before, a little bit after so I can compare. Then we got into this idea of boundedness. So basically, the layman's definition of that is you're not bounded if the graph in your range, your y values get to infinity or negative infinity. Does that make sense? If because infinity is unbounded. I'm infinity all the way up there. That's unbounded. It doesn't matter what happens in the middle. However, if I have a maximum min in the range, a value for which there are none higher and none lower, even if they are included or not, doesn't matter to me. This graph right here, if this was my range, in this example, that function that has that range is definitely just bounded, period. Bounded means top and bottom, bounded. This one is not bounded. And I know that seems weird, but remember it's a technical definition. Bounded means both. What would this one be? Bounded above, okay? We don't usually come in and say this is not bounded. You usually go bounded, bounded above, okay? This one would be bounded, if I had that as my range. It doesn't matter that they're not included. It doesn't, the graph never makes it higher than 10 and lower than negative 10. It's bounded on both the top and the bottom. And then this one, bounded above. Doesn't matter that I skipped some things. We don't care about what happens in the middle. All we care about is that up here on the top, the highest y value that I get is 4. And I actually could be not including 4. There is a value for which there's none that get any higher, so it's bounded above. Okay? So our three terms, bounded means both. Bounded above, only on the top side. Bounded below, only on the bottom side. And then if I have something that has negative infinity to 2, union 5 to infinity, if that was the range, what would you call that one? Unbounded, because the ends managed to make it to infinity and negative infinity. So that's our boundedness. Yes. Because you know, you're never getting higher than that. It doesn't really matter whether there's a global max on the graph. You never get any higher than 10. So I could be bounded, but still have no global maxes in this, which is what this one has. This graph right here must have no global maxes in mins because it never gets higher than 10, and 10 is not included, so it can't have an actual highest y value. There's no global max, but it is bounded. Okay? All right, so is this where we stopped the last time? So we recapped that. Now we're on example 5. So I'm going to let you try this on your own first. So you're going to go ahead and these are the pictures we already had. We actually did this on the other page, but don't look at the answers. Try to do it without looking at it. Write the range of each of these. Use what the range is to determine if the function is bounded, bounded above, or bounded below. Okay? Go. Okay, are we ready for me to show you the answers? All right, so I'm going to unfreeze the whiteboard. Question. Everybody good with bounded, half bounded, or bounded, bounded below, bounded above, and then range. All right, so let's slide down. Here's our example 6. We want to find all extrema on the graph below. All right, first thing that I'm going to do, we're kind of work through this together, is let's go through and talk about absolute first, because I think that would be kind of the easiest to do. What can you tell me about absolute max? There is none because this goes up to infinity. So no global max. What can you tell me about the global min? There is one. What is the location? What is the location? 6. All right, so the global min. Now, I could just say the y value, the global min is f of 6, but hey, what did I give you? I gave you equations over here on the side. So even if I was going to say the global min is f of 6, I'm going to go, oh, wait a minute, I have an equation. What is f of 6? Which piece do I use? The last one, so it's 10 times 6 minus 69, or negative 9. Remember, you're not allowed to do looks like, so you should verify. You might get lucky with looks like, but we should check with our formulas and make sure we have it. So the global min is negative 9. Where does it happen? At x equal to 6. All right, now we're going to start doing the relative ones, and those are typically a little bit harder because there's more than one of them. And we're only looking at a portion of the graph. So let's start with relative. Let's do maxes. Start on the left. I like to start on the left and kind of scan through. Anybody see a y value that I would consider to be a relative max? But what is the relative max? What's the y value that I would consider a relative max? 8. Up here I have this point right here, clearly on a little section of that graph. 8's a high point. Okay, there's none higher than 8. So I would say relative max of 8 at, now here we get to our little constant section, for what x values? Negative 10 to negative 8, non-inclusive. All right, and let's actually do all relative maxes and mins. If I go left to right, I can hit them all. Are there any, does that also have something to do with relative mins? Because not only is there in this little section of the graph none higher than 8, there's nothing lower than 8. So I actually got to count that as a relative min of 8 at x element of negative 10 to negative 8. All right, what's the next key thing that I would consider to be a relative max or a relative min? Negative 6. Can we verify that it's negative 6? Because when I plug in negative 4, where do I plug in negative 4? Oh, well, I don't plug in negative 4, but both of these would be the same. I'm sorry, negative 6. If I plug in negative 6, is that going to work out? Because, yeah, negative 6. So we're okay with that. So we have a relative min of negative 6 at x equals, is that negative 6? Negative 6. My eyesight's going when I look at this thing. All right, what's the next y value that's important? Is it relative max or relative min? Kind of both, but I'm going to do them separate. You'll see why in a second. Let's do relative min of negative 2 at x, an element of, what should I do? Both exclusive? I would actually include this one because look to the left, look to the right. There, it is higher than anything, or There's none higher than it. The one over here on this right side, it goes down. So it's still a, oh, sorry, never mind. I'm doing relative min. Open, relative min, which should foreshadow my next one is relative max. Now I'm going to put a bracket. X element of, does everybody see the difference between why I want to do a bracket versus why I want to do a parentheses for one of those? It all depends on what happened on the right side, whether it went up or it went down. All right, what's the next one that's important? Next y value. -8. Relative, what is it? Relative min of -8 at x equal to 1. The next one, relative max at, well, let's check it out, -6. We're thinking it's, well, it's happening where? At the switching point? Where do you switch from one piece to another there? At 5, and if I plug in 5, I get 2.5 minus 8.5. Is that -6? Okay. Any more? Well, I'm doing relatives. I already did my globals. Right. If it is, it can be both a global and a relative. Yes, you already, because I only up here I only did global. Now I'm doing relatives. So this is a relative min of -9 at x equal to 6. And then that should be it. So list them, and if it is a global and a relative, you got to list it in both places. Mm-hmm. What do you mean all the points that are on there? I think you're using points too many times. The actual point, what do you mean the actual point? Like the coordinates of the points? Oh, you're saying that if I look at this, well, what if I had not put an actual point there? What if I just had it coming in and going down? Would you skip it? Because I'm looking at a local section of the graph and I'm saying, hey, does that look like a low point on that little local section of the graph? And if it does, I include it. Doesn't matter whether I actually put a dot there or not. I'm looking for high points and low points on sections of the graph. Oh, if there's like a gap or something, or I'm sorry, I'm having trouble understanding exactly. I'm sorry. You want to draw a picture, or? I'm gonna pause for just a second. All right, so the question was to look at on a section of the graph, why don't we have, like, why don't I look at this local section? Why don't I look at that section and say, what's the high and the low? Which would then make pretty much every point a high and a low on something. But we don't care about, when we say local, we're looking at places where the graph does something like it changes direction. This went from decreasing to increasing, and the important point is where it changed. Or it came across here, and look, there's a horizontal section. So it changed from increasing to horizontal, and then all the points on the horizontal section are going to be important. But nothing in the middle of that would be considered important enough to include. Okay. All right, so that's the end of that page. Let's go to the next one. I'm still recording, yes. Let's not have a comment. All right, increasing, decreasing, and constant. So this idea of extrema is really directly related, springing off that question, to where a function is increasing, decreasing, and constant, because a lot of times where you switch this increasing behavior, decreasing behavior is where you have some type of an extrema that you're going to be looking at, a relative extrema. What kind important thing to remember as you're doing this, what we're basically looking at is we're saying on this interval, so we're going on the interval, and in this case we're going A to B. On this interval, I want to know what is the behavior of the y values. And the behavior of the y values, we always read left to right. If I were to compare the y value of the first x that I get to the y value of the second x that I get to, notice the second y value is always higher than the first x value. Therefore, the function is considered to be increasing, going up from left to right. And this is true, technically for these, I should be saying, for all x in this interval, this is true. That statement that the y value for the first x you encounter is smaller than the y value for the second x that I encounter. That's what I'm looking for increasing. Okay, why am I talking about this in terms of function notation? Because sometimes you don't have a picture. You're like, this is obvious. Yes, if you have a picture, this is obvious. If you don't have a picture, you have to compare the y values and see what happens. All right. The other thing that we want to talk about with this, kind of relating it to something we've already been discussing, what if I were to look at the average rate of change, also known as the slope of the secant line between those 2 points? Yes. It would be positive, okay? So if I were to pick any 2 points in the interval and draw a secant line and calculate its slope, I would get a positive slope. Therefore, it's increasing. All right? Any 2 points. If I pick any 2 points and I draw the secant line and get a negative slope, then it is decreasing. And then if I pick any 2 points and I try to calculate a slope, but I get 0, then I would be constant. All right? Slope positive, slope negative, and slope equal to 0. And going even further into our calculus world that we are preparing for, if I were to not even be concerned about the slope of a secant line, if I were to draw a tangent line at a specific point, a tangent line at a point, so maybe right here I draw this tangent line. This is going to take out the comparison part. What would be true if I'm on an increasing section of the graph? What would be true about the slope of the tangent line? Well, the tangent line physically would be above in this case, but it would be positive. The tangent line slope would be positive. And this is where the calculus is going to come in. I don't actually have to do a comparison. I can actually figure out whether the graph itself is increasing through that point by simply looking at the slope of the tangent line. I don't need to have 2 points. I can look at 1 point and its slope of the tangent line and figure out whether or not the function itself is increasing or decreasing or constant. So this idea of slope and its relationship to the behavior of the graph is going to be important. You can only change your increasing and decreasing in constant values at an extrema. And note I'm going to underline this word in that sentence. That's the graph of a what kind of function? Continuous function. Okay? Which means I don't have anything weird like these jumps and gaps and asymptotes and all that stuff going on. If it is continuous, the only time you can change increasing and decreasing has to be at some kind of a relative extreme. However, if I have a discontinuous function, something that has holes, jumps, gaps, things like that going on, you can also change at any type of discontinuity. Okay? Doesn't have to actually be an extrema. I mean, just as a simple example, if I have a graph that increases, has a hole, jumps down to here, has a hole, and then goes off in this direction, I could change, I may not change. Notice there is no relative extrema here. There's no global max, there's no global min. There actually is no extrema on this graph. However, it did change from increasing and decreasing because there was this jump into the behavior that can change at a discontinuity. Everybody good? So we're going to introduce another idea that's coming up. We're going to, instead of doing sign charts tell you where the function value
unusual positive, negative, 0, or undefined, we can actually also do what we consider to be sort of like a sign chart, where I put the critical numbers where I might switch increasing and decreasing in constant sections, and then label it as, instead of a sign, S-I-N, I label it as, oh, hey, function, increase, decrease, steady state. And you just kind of go through and put relative extrema on there for your kind of situation. We will come back to this. This is why I'm going to start talking about in this that there are critical values for increasing, decreasing, constant status change. So it's going to be very similar to the idea of doing a sign chart, except it's going to be a increasing, decreasing chart kind of idea. It's going to be like a slope chart. And the nice thing about it, we actually do sort of still consider it to be a sign chart, because where the slope is positive, the function is increasing. Where the slope is negative, the function is decreasing. Where the slope is 0, it's staying same. So there's this little idea, it's still a sign chart-ish. You'll do sign charts more with this when you're in calculus, but also just more or less increasing, decreasing, constant. Right. All right, so, and again, a lot of times when we're doing this, yes, there is this whole discussion about increasing with a closed bracket, and I actually, when I did this little definition up here, I did say on the interval closed A to B, but I will say that in most situations in calculus, they kind of don't worry about the bracket part of this. They pretty much go, give me the open interval for which the function is increasing. And they take out the kind of the point that's the extrema. They're not even going to consider that, really. There are some that argue that you are increasing. You can be closed. Like I would say here, I am increasing from A to B, and I would do inclusive, because all the points after A are a little higher, all the points before B are a little lower, so it does increase. But a lot of times in calculus, we don't really care about that part, so we'll usually go open interval. So notice that in all of my directions, the directions will say, state the open intervals for which the behavior occurs. Now, just like with the maxes and the mins, the max is the y value, the location is the x value. Same thing is true for the increasing and decreasing. The increasing is the y value behavior. Your job is to tell me the location, which is the x values for which it happens, right? So if I was looking at this kind of example that we have here, and usually these are not sets, we're just listing the intervals for which it's going to happen, we would say f increases for the intervals, and let's name the intervals. What are the intervals for which I am increasing? A to B, that's 1, comma, C to D, C to D, and is that it? All right. Does it bother me in between C and D that I kind of look like my slope leveled off right here? Not really, because the value of this slope is, even though it's 0, it's still, this point is still higher than the ones that came next to it. And the ones that came after it are higher than that. So it's still in an increasing section. It doesn't really matter that the slope was 0 there, okay? That the tangent line would kind of go across horizontal. That doesn't bother me that I go horizontal for just a little blip, okay? That's not constant. That's just, hey, I slowed down a little bit, and then I sped back up again. But I was increasing the entire time, okay? So it would be increasing. And then we would say, and you could say instead of a comma in between them, you could say for the intervals this and this. This is English now. This is not and as in the intersection of two sets. It's and as in this one increases here and it increases over there. All right, f decreases for the intervals. What are my decreasing intervals? B to C and D to E. If I were to think of this like a kind of sign chart idea that I'm going to be doing, kind of making this relationship, this is
kind of a function is this? Assuming that, well, I guess it would be continuous on its domain. Pay attention out there. It's continuous on its domain. If it's continuous on its domain, for where can I switch increasing and decreasing? Only at extrema values, okay? Notice that if I were to name my extrema, I have them all listed up here. We have absolute min, we have this A. Then we have a critical value at B, a place where you would switch. Critical value at C. Another critical value here at D, and another critical value. And I'm going to put E in here, even though it's not a relative min, and it's not an absolute min, because it's where the end of the discontinuity starts. So on this little chart, we could kind of go F does not exist, right? Over there, discontinuity. What's happening at A? Is it's going to start increasing. Now notice I'm going to kind of leave that off because I'm really more concerned about the open intervals for which it happens. So I would go, it increases, then we decrease, then we increase, then we decrease, and then we do not exist. That's kind of like your quote-unquote sign chart for increasing and decreasing. If I then wanted to classify, let's take a look at what's happening at these locations. What must be happening at x equal to A? Do I know anything about this because it's D and E and then increase? Not really sure I know much. Could be a, what's its only choice? It's an endpoint. It's an endpoint. What's the only thing an endpoint can be in terms of extrema? Absolute. And since it increased after that, the only thing that this could be is an absolute min. Okay? How would I know it's an absolute min? I would not know simply from this chart. I'd actually have to know the actual y value to know it's the lowest one and all that stuff. So it can't be anything. We'll just put endpoint may be global min. We would have to investigate for that. However, when I get over here to B, I'm increasing before, I'm decreasing after. What must be? It has to be a relative max at that location. Has to be. Because the function is continuous in that little section, and it was increasing before and decreasing after. That's it. That's my only choice. What must there be at C? A relative min. At D, there must be a relative max. And then at E, it's an endpoint. What's its only chance of being something? Global. And given this chart, does this chart actually tell me global though? No. What this chart does, where I'm switching increasing to decreasing, will tell me where my relative extrema are. That's what it tells me. Okay. Everybody good? All right, so now we're coming back to our little example that we've been working on. We're going to do the open intervals, open, of increase and decrease for the functions that I have listed. So in this first one, let's do f increases for what? 0 to 1. What does f do for the other interval? F decreases for 1 to 2. And notice this is the nice thing about calculus. We don't really care about the brackets, parentheses, issue thing, inclusive, not, we don't. We do open intervals, and we're fine. Over here, what would I say for this? F increases for the entire time, 0 to 2. What about this one? F do I have to break that one up? I actually don't. It increases and then increases again. Yeah, for this example, you could actually go 0 to 2. Increases for 0 to 2. However, I will say that a lot of times and it wouldn't necessarily be wrong for you to say it increases for 0 to 1 and increases for 1 to 2. Okay, because something weird is happening at 1. So they do sometimes break that up. What I want to caution you on about putting them together is this. What if this is my function? Or not even if I was doing 0 to 2. Let me do the same kind of 0 to 2 thing. So it starts there and ends there. So it goes from here, that's 1, and that's 2. What would I have to be very careful about, Avery? Yeah, this idea, I couldn't say here f increases from 0 to 2, because it actually doesn't. It increases, drops down, and then increases. And so that's why a lot of time when you see something like this, even if this is true, they usually don't put it together. They usually pretty much always come in and say, I'm going to go with that version of it. Because something weird is happening, there's discontinuity.
All students from George, Petersburg, and Oakland, teachers putting in the students at the return, students in Charlotte, Oklahoma.
Yes. Okay. So we increase for those two separate intervals. All right, let's come down to our little example that we've been working on. All right, we want to state the open intervals for which I have increase, decrease, and constant for the function below. Let's do the increasing first. F increases for -6 to -4. Is there another one? 1 to 5. And 6 to infinity. Am I good? And remember, what are these intervals? These are x or y. These are x values. These are the location for which the y's have the behavior of increase. Okay, we would say f decreases for, what are my intervals of decrease? And then I do have some constant sections on this, so I would say f is constant for -10 to -8, -2. And I don't have to worry about bracket parentheses stuff because I asked for open intervals for which it has this behavior. And this is kind of a review because we kind of did that when we did parent functions, right? All right, now, discussion of bracket usage for increasing, decreasing, and constant. It can be a consideration. But most of the time they will ask you for open intervals. But most of the time you will be asked for open intervals. So you don't really have to worry about that.
When will you not use it?
When we have to be like brackets used, I'm leaving it as a possibility because you might leave my class and go to somebody else, and they may choose to say, I would like you to know when you should include or not include based on the behavior of the graph. Just as an example, if we look back at the one that we just did, if I was doing brackets, like here, this would have to be, this is where you're like the putting it together. If you had this, I would put it together. Over here, I would include, like I would change this to bracket 1 to 2. But here, I would do bracket 0 to 1 parenthesis on it. And so it's stuff like that. It's just that it's such a little thing in calculus, we don't worry about it. And I'm not going to worry about it either. Because if they're not going to make you do it in the AP, I'm not going to make you worry about it in this class. All right. Where do relative maximums occur? What must the behavior of the function be before the max versus after the max? Okay, when f of x switches from increasing to decreasing, and then I'm going to put right below this, because this is kind of previewing your calculus. You're going to be so good at calculus when you get there. In calculus, we would say when not the function switches, what does calculus look at? The slope. The slope switches. And what's the slope switching from? From positive to negative. That's how we do it in calculus. We give the slope of things in the independent slope. But that's what we're doing. The derivative. The derivative function is a function related to the slope of the tangent line. Right? Relative minimums occur when f of x switches from decreasing to increasing. And again, we'll put the calculus when your slope switches from minus to positive. Can a relative minimum occur at infinite continuity? I have one no. What about the rest of it? Can a relative minimum occur at a discontinuity? Sometimes. As long as what? As long as there has to be no regional discontinuity. It's got to actually be a point. Okay, there's the first thing. It can be a discontinuity, but it can't be a, what do we call it in domain? Domain restriction. Because domain restriction, there's actually no point there, right? Either there's a hole with no point, a vertical asymptote, or a gap or something like that. All right? So if you have a discontinuity, it can still be a relative minimum as long as there is actually a point there, okay? So I mentioned that. I say it occurs when f of x switches from increasing to decreasing. I should probably put if there is a point. If in domain. How about that? Can we do that and you understand what I mean? If it's not an x value in the domain, it cannot be the location of a relative maximum. It's actually not actually a point. You have to actually be a point. You have to exist in order to be candidates. Does that make sense? All right. So now the next part of this. So we have our functions. We talked about domain. We talked about range. We can find function values. We've got the highest, the lowest. How they're increasing. They're decreasing. But that's not, now that they're a non-linear function, functions actually have curvature. Okay? So we have a characteristic that we like to look at, which is called concavity. Concavity has to do with the curvature of the function. It has to do with how fast the function is changing at any given time. If I was looking at a function like this, how fast, what's happening as I go through this function? At each point, am I speeding up or am I slowing down? I am speeding up. It's getting more and more steep as I move around. So the function itself, it's increasing. This is increasing at an increasing rate. Increasing at an increasing rate. It's like the exponential growth curve. That one is clearly increasing at an extremely fast increasing rate. Parabolas are increasing at an increasing rate too, just not as fast as the exponential one that we looked at. Right. And half of it is decreasing. But Yeah, let's see, my picture here right now is increasing at an increasing rate. What's this one doing over here? Increasing at a decreasing rate. Getting less steep as I go across. Okay? Yeah, like the square root function would be an example. And so this really it's not the increasing part that I'm looking at here. What I'm looking at is the fact that it's increasing at an increasing rate. And if you look down here kind of at my picture, if I were to draw a tangent line in, where does the curve go compared to the tangent line? It curves up above the tangent line. Does that make sense? So this type of behavior, when you are an increasing rate, you're going to be considered to be concave up. The curve curves up from its tangent line. Yes. How would you graph? What do you mean? The fact that the curve goes, that it curves up, I know that it's going at an increasing rate. That's what's making the curve bend, because I'm speeding up. Okay? What's making this curve bend? The fact that the rate is slowing down. So now look at where your tangent line is. The tangent line or this function? Well, it could be any function, like square root would be an example. What do we call it if it curves down from its tangent line? Concave down. And then this, I want to just make sure I show you, concave up. It does not have to be increasing at an increasing rate to be concave up. What's happening over here? This side of this function is decreasing, okay? Nope. It's decreasing at an increasing rate. Now let's talk about why that's an increasing rate. In this, what do we know about the slopes on that side? The rate is the slope. Okay? The slope over here on this side is what kind of a number? It is negative. As I move over to this side and I start looking at the slopes, they are becoming more shallow, but that means that they're becoming closer to zero. And when a negative number gets closer to zero, it's not decreasing, it's increasing. So this is a decreasing function that is decreasing at an increasing rate. The easy way to remember this is if I were to draw a tangent line, where does the curve which direction, up or down? On the tangent line, it curves up. So that's how I know it has to be this increasing rate idea. So this graph right here, this parabola, is actually concave up for the entire way. We would say this is concave up for negative infinity to infinity. What's the difference here? It's not increasing the entire time. What is the function itself doing? F is decreasing for negative infinity to, is that 4? Okay, 4. And increasing for 4 to infinity. Those are two separate behaviors. There's increasing, decreasing, and then there's a reverse of our increasing and decreasing, which I call quadratic. And because it curves up from its tangent line, then you are considered to be concave up. Good? And just to, I showed these as my first examples because invariably somebody wants to tell me that this is concave right. And I'm like, that's not an option. You either curve up from your tangent line or you curve down from your tangent line. You're above your tangent line or you're below it. There's no left, right in there. Okay, it's either up or down. That's your only option. Say what? Don't be funny. Don't try. And then this graph right here, this function, even over on this side, right? So this is increasing at a decreasing rate. Over on this side, I am decreasing at a decreasing rate. And you're like, well, why is that at a decreasing rate? Again, it has to do with the negatives. If I am negative and I look at the slope over here, this negative, not too much. What happens when I get over here? it becomes more negative. Does that make sense? I'm getting steeper in the negative direction. Steeper in the negative direction means I'm getting, in magnitude, a bigger negative number, but a bigger negative number is actually decreasing. Negative 100 is smaller than negative 10. Everybody agree with that statement? Okay, hopefully. That's why I'm decreasing at a decreasing rate. The tangent line, the function curves below its tangent line. Okay, concave down. All right, so here's my little graph that's right here. Now notice that, am I considering critical values for switching concavity to the extrema? Nope. Those are only critical for switching increasing and decreasing. There are points, like this point B right here, it's a place where I'm switching my curvature. That is not an extrema. It could be an extrema, but it is not necessarily an extrema. So this point has a special name. This is called a point of inflection. That is a point at which you are going to switch your curvature. You're going to switch how fast your rate is going. Are you going at an increasing rate or are you going at a decreasing rate? So if I was looking at this graph, I would say this function f is concave down. Let's start with what intervals is it concave down? It's concave down for concave down. A to B, I need it to curve down from its tangent line, so A to B. Okay, now don't do the extrema because it's still concave down there. If I were to actually put a tangent line at the extrema, it still curves down from it, so it's concave down there. Right? Where do I start being concave down again? C to D. Okay. Where's another one? Any more? P to Q and P to Q. Okay. F is concave up. Where am I concave up? B to C. I will say that anytime this cusp, you're like, hey, but it's also concave up over here. That cusp is kind of like a discontinuity. Right, remember, what does I say about the cusp? It has no slope, right? It has no slope because it switches. And so they will break that up there. That will consider to be something important, kind of like where you have a hole or something like that. So I would do D to E, and I would do E to P, E to P. I would split at the cusp. And that has to do with because you cannot have a slope, no slope at a cusp. Now let's talk about points of inflection. Points of inflection, I have the definition right here. Points of inflection are a point where your concavity switches. Where your concavity switches. Okay? So the points of inflection for this example are at what x values? Where do I switch? X equal to B, C. Yeah, because it's down and then up. Doesn't matter that it's a cusp, it just needs to switch. Okay, and it's a point. It has to be a point. So D. What about E? E's a cusp, but does it switch? No, it's up and then up, not a point of inflection. Okay, and then P and P. I know, because I'm trying to make it obvious. All right, so again, is this idea that you just have to switch. There is a point somewhere, if you have a change in curvature, for which you will switch. Now, what is it that calculus is going to do for you? What is calculus? How do you find the extrema? How do I find these points at where I switch increasing and decreasing? How do I find these points at where I switch from my concave up to concave in? That is what this calculus is. And so what we will we'll be able to do in our class is we can calculate zeros, right? How to calculate zeros. Well, but zeros on a graph are specifically with x-intercepts, which I find by setting y to 0. I can choose a y value and say, hey, tell me all the x values that have a y value of 5. Right? Only by plugging in and solving. But if I were to say, tell me the x value at which you have a maps, and you don't actually have a picture to look at, how do you find it? You can't. Unless you do it approximately, which is use your calculator. Calculator finds for you. Which calculator doesn't find you exactly, your calculator finds an approximation for you. And then your calculator doesn't even help you with points of inflection because it won't find points of inflection for you. You don't have that as an option on your calculator. So you have to have some calculus in order to do that. Oops. All right. Stop flipping. Go on. This is the page we were on. And there we go. All right. So example 11. All right, so if I give you something like this, I pretty much have to label and put points of inflection on there for you. You can't find them unless I tell them to you. So pretty much anytime we're going to talk about concavity, because you're in Algebra 2, you're in the toddler math version, I'll tell you where they are. All right? If I were to choose in this picture where the points of inflection would be, where would you see that there are points of inflection? The label one, like, hey, there's one here. There appears to be one there, and there appears to be one there. Do you notice I did not put a dot anywhere close to an extrema? There's a difference between me asking for extrema and asking for points of inflection. They are different things happening. Extrema is where you switch increasing and decreasing. Points of inflection is where I switch concave up, concave down, and vice versa. What about in this graph? Do I have any points of inflection here? Yeah, I have one here. Well, you have to have an equation to find it. Yes. Can you be an extrema and a point of inflection? Yes. Can you be an extrema and not a point of inflection? Yes. Okay. Unless I tell you you need calculus, which you have to look at. Notice that concavity, the point of inflection is where the slope, as you were increasing at an increasing rate, and then you were increasing at a decrease. So you're looking at the slope changing from increasing to decreasing. Oh, wait a minute. If I could actually find the function that is the slope function, then I would have a way to find the math and going on that, and that would come in nicely. That has a lot to do with looking at the rate and how it moves to the rate. All right. And I already did that one. Can I say see previous page? Okay. Critical numbers for concavity. Just like when we had these little sign charts for positive and negative and 0 on the function, then we had a quote-unquote sign chart for increasing, decreasing, and constant. We are now going to do a quote-unquote sign chart for concave up, concave down, and points of inflection. Same kind of idea. This idea of a sign chart is going to come into play. What are my critical numbers for my concavity change? Is extrema going to be included in that for critical numbers? The answer is no. You can change concavity at a point of inflection, or constant that changes that into constant that exists at the point of inflection. So point of inflection is right in there. But what else can I switch at? Restrictions and discontinuities, depending on what's happening with the jumps and all of that stuff. I could have a graph that comes in, does this, comes down here, and does that. Did I switch concavity? Do I have a point of inflection? Oh, did I ever say that points of inflection had to be continuous at that point? I did not. I said that it's a point of inflection if it
switches.
So this does have a point of inflection. It happens to be that at x equal to whatever this value is. We usually go at x equal to 2. There is a point of inflection. But what if I had this? Is there a point of inflection?
No, because there's no point there. Okay?
So that's the difference between it. But you can switch at restrictions, discontinuities, cusp, which are points of inflection. Okay? So points of inflection, any cusp, any restrictions, any discontinuities. All right, in the remaining portion of the time that we have, which is really nothing, but while we're on snow,
Okay? Let's talk about what's going on. One, you are going to finish this packet. This packet has a whole bunch of answers. 1, 2, 2. 2 examples where you can run through everything we talked about in Samuel. So you don't have to do that as practice.
that's number 1. The quiz that we were scheduled to have today is going to be the first time I see you when you come back. And this goes for the people listening on the video as well as you guys. Whatever day we come back to school, we are having a quiz. That quiz is now going to cover 3-1 through the end of this packet. I will post a T. Okay? So it includes all the characteristics. The transformation notes. If we are not here on Friday, if we are here on Friday, what are we doing? We are taking a quiz, right? If we are here on Friday, we are taking a quiz. Take your stuff home. If we are not here on Friday, I will be posting a video on transformations. So go to It's Learning. It'll have a link to YouTube for you to watch. Probably about a 40-minute video, 40-minute video. There will be a note packet kind of along these lines that I will put online for you to print, for you to go through. And it'll tell you what your homework is. I may adjust this. I have to see what happens on the video, whether I'm going to leave that as your homework to work on over the weekend or not. Yes. You will have the quiz. 3-1 to 3-3. Can't have the test. I can't have the test because we'll see what goes on. We'll continue with distance learning the more we're out, but we will definitely at this point, the first time I see you back, have a quiz. 3-1 to 3-3, or 3-1 to 3-2. Sorry, 3-1 to 3-2. Well, this test is, like, if we come back on this day, I'll probably adjust it at that point. Because I want to be able to grade. I have to teach transformations. I have to make sure you get transformations before I test you on it. So, the test may move, but the quiz is the first day back. Got it? You know what your homework is. You have some bookwork up here for tonight. Hold off on this bookwork. I'll take it back. You do not have that. Then, all you have to do is the 2 problems in the packet, and then you're going to watch the transformation video if we miss Friday. Study for your quiz. Huh? It's not listed, no. But I'm telling you right now. I'm telling the people on the video right now, do the 2 problems at the end of the notes.